All right, shall we start, Benjamin?
Yes.
So we are very happy to have Benjamin McMillan from IBS Center in Korea telling us about foliation surgeries and Godbillon-Vey spheres.
Okay, thank you for the invitation. So let me start. Let's say we have a smooth manifold. I just want to recall quickly the definition of surgery. So we have a smooth in manifold, let's call it M, and an embedded sphere. So that's our setup. And we also need to have a trivial normal bundle. So it's a somewhat special situation, but let's take it as it is. So we have the K sphere, and its normal bundle is this complementary disk bundle, which is trivial, embedded into our manifold. Then the manifold surgery long phi is the manifold, let's call it M prime, where we take M, we cut out the, sorry, someone's a little image of phi, and
Okay.
then,
Sorry I'm late.
right, um, we cut out, so we cut out this sphere times a disk, and the idea is we glue in a disk times a sphere. So kind of you're gluing in sideways. Um, Hi, Eric, I think your speaker is very loud. Thank you.
So sorry about that.
No,
It's
no worries.
fixed.
Okay. Um, so we're cutting out some essentially we're cutting out this sphere and we're gluing in a disk to well, we can say why in a minute, but we're using this fact. We're using that the boundary of uh, the sphere times the disk is equal to the boundary of the disk times the sphere. Um, and the point is if the core, which would be this central sphere, maybe this times zero, if this represents some generator of the fundamental group, then essentially we have that, what do we call this? Some generator alpha. Then alpha gets killed in the surgered manifold. Okay, so we're starting with a manifold. It has some sphere and we don't like this sphere, so we want to get rid of it. That's essentially the idea. And so here's kind of a simple case, one of the only ones you can really draw. So we start with, say, the torus. That's our manifold. And we're starting with a circle. And our kind of codisk is the lines. So we have the circle times these disks, and we is embedded like this. You can imagine cutting it out, and you have these holes here. You have this open manifold here. And then you glue in sideways, and what you're doing is you're gluing in these caps. So you do this and you get this new manifold, which in this case is, if you think about it, it's S2. Um, and the key point for our purposes is we have here this open region. I'll call it M with a circle over it, is kind of contained in both of them. So it's both in M and M prime. So that's hold on to that fact. And so these surgeries are much related to the theory of cobordisms. Um, so the trace of surgery is along phi. It's the simple cobordism. So if you know about cobordism, simple meaning you can give it just a single critical point. The simple cobordism, um, we call it W M M prime, obtained as we take M, we multiply it times the interval, and then we glue on more than just the sphere times the disk. We glue on the disk times the disk along phi itself. And here we're using the fact that the boundary of the disk is the sphere times the disk union the disk times the sphere. And so we're kind of gluing along this region, and so that's somehow attaching this region. We use phi to glue. Okay, so here's my kind of cartoon of we take M, choose a better color, take M and times the interval. So here's M times the interval. And here's you're attaching disk bundle, disk bundle over the sphere. And then you're attaching the disk times disk here. Which this perspective makes it pretty easy to see. For example, you might worry about the corners here. It's not a smooth manifold, but you can just like take a little rounded submanifold and then it's smooth. And so you don't have to worry about making sure your surgered manifold is smooth again. Just to go back to our original example here, let me draw that. Here's the torus. I've kind of opened it up. So identify this end and this end. Here's the interval that we've multiplied by. And here's the disk times the other disk that we're gluing in. And if you think about it, you have here the sphere where this side is identified to this side. So that's the inner boundary is the sphere there. Okay, and so the corollary is cobordism invariants are surgery invariants. So, and there's incidentally a converse. If you have a cobordism, you can break it up into these surgeries or these traces of surgeries. So there's a classical question, which is when is a manifold null cobordant? So when is a manifold bound a larger manifold of one dimension up? And that's the same by what I've claimed above, is that there exists a sequence of surgeries to the sphere of the same dimension. And there's various classical obstructions like the signature, the Whitney numbers. So, now we can, so the point is, if these numbers are not zero, then there is no null cobordism. So one way to kind of guarantee that these numbers vanish is to assume that your manifold is stably parallelizable, which is just to say that the tangent bundle of M plus any trivial line bundle is itself a line bundle, a trivial bundle, sorry. So this process of adding a trivial bundle is stabilization. And so if up to stabilization you're trivial, then you're stably trivial or parallelizable. And that's like maybe a surprising condition if you haven't seen it. So one example is if you take an orientable surface, if you embed it into R3, then its normal bundle, you can take, say, always the outward pointing normal. And that's a trivial line bundle. And its direct sum with the tangent bundle is, if you think about it, just the tangent bundle of the ambient space, which is trivial, restricted to your surface. And so, as I mentioned, this condition guarantees these signatures and such vanish. So there's a theorem going back to work of Milner and then Wall and also Milner again, that if M is stably parallelizable, then it admits a sequence of surgeries. So you start with your manifold, and the idea is let me say the statement first. You do a sequence of surgeries and you end at the sphere. And so the idea is you do the surgery below the middle dimension. Okay.
And can I clarify? Do you only need to stabilize once for this theorem of Milner and Wall?
So this stable parallelizable condition. So to be stably parallelizable is you add a trivial bundle and you get a trivial bundle. It turns out to suffice to add a line bundle.
I see. Thank you.
Yeah. That's in Milner has his kind of original paper about this. What's it called? A procedure for I forget the name. A procedural for modifying the homotopy of manifolds or something like that.
Cool.
And so he discusses that there.
Is there a condition on dimension?
I don't. Let me think. Let me finish the idea and then I'll answer that. I think I see what you're getting at. So surgery below middle. So the point is for generators alpha and pi k, let's say below middle dimension. The kind of the stable condition, so being small plus stable means that you can kind of find a representative alpha. So of your homotopy class with trivial normal bundle. So that means you can do the surgery and kill this class. And you can furthermore, if you're a little careful, do it in a way that preserves so that this has trivial normal no, stably parallelizable, then the next one will also be stably parallelizable. So you can preserve that fact, which lets you continue doing surgery, and you can kind of inductively kill all of the homotopies. So up to the middle, the middle is kind of very tricky to deal with, but Milner and Wall can do it. And then from there, you have kind of half of the homotopy groups vanish. Then you can use Hureyevich and Poincare duality to say, oh, actually, they vanish all the way up. So then you have and then you use Hureyevich again, and you get a homotopy sphere. And then you can use the Poincare, the various proofs of the Poincare conjecture. And so these homotopy spheres are topological spheres. And luckily, I mentioned this to Sam, kind of the application I have in mind is in dimensions 5 and higher. So you kind of have the more classical 50s or 60s version of the Poincare conjecture. Does that answer your question?
Yes, it does.
Okay, thank you. So yeah, it's important to me that these surgeries are below middle dimension. So I kind of want that to be the case. Um, so that's part one. Let me, I guess, are there any quick questions before I move on? Any other questions? Okay. So let me just very quickly say some words about foliations. So as you'll know, a regular foliation is some kind of you have a manifold and you partition, maybe you can't see my hands. You partition your manifold into a disjoint union of manifolds of codimension Q. It's for me easier to speak of codimension, where these are locally embedded. Um, right. Thurston describes something about how can you lay fabric, right? So you're breaking your manifold into these slices. And so there's several equivalent descriptions of this, but one that I'll use is that a regular foliation is you have an open cover by some open sets of M, and you have charts. So to RQ, this Q is the same codimension, which are submersions. Uh, and you have coherences. Some way to coherences are transitions gamma alpha beta from U alpha U beta to diffeomorphisms of RQ. Although really I want like germs of diffeomorphisms. Um, so we don't have to worry so much about domains and codomains, such that the charts satisfy this transitions. So the charts kind of agree up to these coherences. That's why they're coherences. And this cocycle cocycle condition beta gamma alpha delta. So this one's hopefully not a surprising condition. It's it's a cocycle condition. Um, and so the point of this definition is that you have these charts, and the point is the level sets of alpha are the leaves, and the gamma kind of force them to piece together. Nicely. That's why I call them coherences. And so you can think of this as a generalization of smooth manifold charts, right? So if you have a manifold of dimension Q and charts of dimension Q, then this would be a foliation of codimension Q. Uh, sorry, the manifold charts you can think of as maps to RQ. And the change of coordinates, which is part of your definition of being a manifold, are these coherences. Um, and so that would be a foliation of codimension Q, somewhat confusingly, where the leaves are points. So this is what's called a point foliation.
Are you suggesting we don't need M's atlas? That we could just use this foliations atlas?
That's a very interesting question. You need the IMS atlas here for submersions.
Okay, yeah.
For that to make sense.
Right.
But that's a very good question. I'll answer it. I'll get back to you on it.
Thanks. Yeah.
So here's an example. Let's take the torus and let's take rational or irrational slope foliation. And so here's one chart. Here's another chart. It kind of wraps around. Um, and here's F1. Sorry, it's getting kind of messy. And this one, to have a continuous chart, let's say it goes to here in R1. Is a codimension one foliation. But of course, you also have this overlap, which is somehow on the gray part, it's here, on the green part, it's here. And so that you're gonna have the transition gamma kind of gluing those together as well. So that's part of the data. And the non-example would be something like this, where the leaves of one chart don't line up with the other. So there's no way to have transitions. So there's a problem for me that regular foliations are too rigid. So famously, S2 has no codimension one foliation, right? Because if it did, this would be a no regular codimension one foliation, because this would be a vector field that's nowhere vanishing. And we know that doesn't exist. So there's various ways to kind of get around this, generally by allowing singularities. And so one solution to this is Haefliger's solution, which is you don't assume that these were submersions. Okay, so a Haefliger structure is exactly the definition above, but with arbitrary continuous maps. So let me go back to the definition. You have a manifold, and actually to your question about charts, you actually here now can take any topological space. So this is something kind of funny about these Haefliger structures. So a foliation or a Haefliger structure is an open cover. You have charts. We get rid of this submersion condition, but we keep the coherences, and that's the coherences become much more load bearing now. You just otherwise you wouldn't be able to talk. Your charts wouldn't talk to each other at all. Kind of for a regular foliation, if you have submersions, you can kind of recover the coherences by, well, like change of coordinates in that sort of a way. So here's one picture of a Haefliger structure. So we take the sphere and take just the height map. So each of these point leaves pull back to a circle, except there's these two kind of necessarily singular points. This is a kind of trivial Haefliger structure because it's defined by a single function. Now, the key feature of Haefliger structures is that they pull back. So given the continuous map M, and this is really the kind of the problem with regular foliations is you don't have the following property. So if we have foliation on some other manifold or space in, and a continuous map into that space without already a foliation, we can define the pullback foliation. Well, the opens are easy. You just take, oh, this is H. Just take the pre-image of your opens from the Haefliger structure here. Your charts are easy because you just pre-compose with H. So this goes from inverse U alpha to RQ. And your coherences are easy. You just, again, just pre-compose. All the data just pulls back. And so for this reason, what? Yeah, so for this reason, the Haefliger has the following theorem that there exists, well, this is kind of a necessary condition for the following theorems. There exists a space, let's call it B gamma Q, that classifies So if you've seen classifying spaces, it's the same statement. So fixed manifold, I'll stick to manifolds even though you can talk about spaces. Fixed M, you have Haefliger structures on M, and let's say up to an equivalence that's approximately homotopy. I'll say more in a minute. This is the same as continuous maps, I don't know, M to B gamma up to homotopy. Oh, at some point I wanted to restrict to orientation preserving, like orientation preserving coherences, just to be kind of safe, not worry about base points or anything. So you can think of B gamma Q U, some universal Haefliger structure, foliation. So I'm going to start just saying foliation because Haefliger structure is too many words for me. And so then the map, this map here is given by, I don't want to call it F, do I? You have a classifying map in here. It gets sent to the pullback foliation. And that's a pretty reasonable picture of what's going on. Oh, and so to describe this tilde here, we say that MF and MF prime, so two foliations on the same manifold, if there exists a foliation extending kind of both of them, so on M times the interval. So you can map M to one end with F. You can map M to the other end with F prime. And this foliation has to pull back to F on this end and F prime on this end. So this is the I would say the kind of proper notion of a homotopy between, or an integrable homotopy, if you like, between Haefliger structures.
Is gamma Q some type of topological groupoid built out of germs? Or...
That's exactly right. Yeah.
Okay.
Yeah, if I had more time, I would say more, but that's Haefliger. I think he just that's a topological groupoid, and he just does the Milner's
nerve.
construction.
Yeah. Cool.
So here's my picture of a concordance. Here we have a foliation that's like this, and here we have foliation that's sideways. And so you actually have to work a little bit hard to find this concordance. So what you can't do is like rotate the leaves, kind of change the slopes like that. That's your first guess. You can't do that. It won't be integral kind of in the time direction, integrable. So you have to do something a little more clever. So you have to spin the leaves in this way. And so you have this central leaf, which is just a closed leaf. And then these ones you spin the other way. So it's just one example. So a concordance class is trivial if it contains the trivial Haefliger structure or foliation. And trivial Haefliger structure, that just means defined by a single chart. Of course, two trivial Haefliger structures are concordant because you just kind of extend whatever, however you want your function across the middle, linearly, if you like. So a little lemma, maybe to give you an idea. We have a foliation or Haefliger structure on the sphere. This is trivial if and only if it's an extension, if it has an extension to the whole disk. Here's my picture. Uh-oh. Um, so think about on the circle, you have this point foliation. Um, One way you can close it up to the disk is like this, where you kind of make some circle and spin around it. So again, you have to work a little hard. Um, but then you can just take some other disk that's a single chart and imagine cutting out that little disk. And what you have is the annulus, which is the circle times the interval. So that's your concordance. This on this circle, it's clearly single charted, so it's trivial. And you can show the converse. A non-example, if we take S2, F sub S2. So S2 is a smooth manifold. We can think of it as charts itself as the charts of a Hifliger structure. So with the coordinate charts as Hifliger charts. That's called a point foliation. And so the reason this is a non-example is that Hifliger structures have a normal bundle. So if you know the normal bundle of a foliation, it's a generalization of that. Or, okay, if you like, we have B gamma Q, which as Eric mentioned, this is germs of diffeomorphisms. There's a map, let me say it this way. There's a map to GLQ, which is just take the differential of the germ at your kind of central germ point. There's a continuous map like that. So you have map of classifying spaces. If you have a foliation that's classified like that, the induced map down here is, so here's the classifying map of the normal bundle. So the point is Hifliger structures have normal bundles. That's kind of, we just need this fact. And in this case, the normal bundle of FS2 is actually, again, kind of confusingly, the tangent bundle to S2. Because, right, the transition functions are exactly the diffeomorphisms of the coordinate transition functions. So that's one way to get the tangent bundle. So if this foliation extended to the full disk, we have, what do we have? We have kind of the associated normal bundle. And this would embed into the normal bundle of F bar, but that's just a rank 2 vector bundle over the disk. So this is trivial. So this would have to be trivial, but it's not trivial. So you have a contradiction. Or more properly, you can say that the normal bundle is itself a concordance invariant, because there's this theorem that concordance of vector bundles implies isomorphism. So that's the more kind of, it's the same statement as what I just said, or maybe it's a more general statement. Other questions on foliations before I move on? So this was our setup going back to surgery. We had a manifold, we had this disk bundle, we cut it out, and then we glued back in something. So like, for example, on the torus, we cut out this disk bundle and got, well, if you take this part and open it up, you get this cylinder. And then after surgery that sits inside of the sphere. Now let's suppose that M furthermore starts with a foliation, right? Then what we can do is take this foliation, restrict it, and then kind of push it forward, or just think of it as living as a partial foliation on our surgered manifold. And we say that a weak foliation surgery is, what do we say? It's any foliation on F prime such that its restriction to the open region is equal to the restriction of the original one. So that's kind of what this picture is supposed to be getting at. Okay. And then a strong foliation surgery is a weak one plus there exists an extension to the full trace. Of our boundary surgeries, boundary foliations. Okay. So let me kind of, you might ask, does this one, can we close up this surgery here to get a foliation surgery? I kind of drew the picture already. You can imagine kind of doing this spinning maneuver again. Oh, this is a top-down view of this one, of course. And so in this case, you can. So sometimes foliation surgeries exist. But it turns out sometimes they don't exist. Okay, and then just
Can I confirm for now, when you say foliation, you mean a Hefflicker structure? So,
yeah,
okay,
I'm dropping all regularity,
sure.
but I am keeping Hefflinger structure. So there are more singular foliations than that. Okay, this is a remark that's not justified yet because I haven't talked about any of it, but essentially by definition, there's this notion of foliation characteristic classes. And then if you take the degree equals the dimension ones, you get characteristic numbers. And then when these are cobordism invariants, so then the characteristic classes numbers are preserved by strong surgeries is the point, essentially by definition. But anyways, if that's, I haven't defined all that, so ignore it. So yes, these foliation surgeries don't always exist. So there's an obstruction, which I call the surgery obstruction class. It's the concordance class of the pullback. So what do we have? We have SK times 0, the core of our surgery, or our surgery region, or however you call it. We have our foliation on F, and so you pull it back to the sphere, and that class is the obstruction class. The point being that if MF and phi admit a foliation surgery, the obstruction class vanishes. So the concordance class is trivial. Okay, and of course the contrapositive of that statement is that the concordance class, if it doesn't vanish, then there isn't a foliation. So it's an obstruction. Um, the picture is we start with MF. We pull back the foliation to this sphere. If we had a surgery, we have this F prime. And so we can pull that surgery back to the the co-attaching region, or however you call it, of the surgery. Right, the thing that we glued in sideways in our surgery. Um, and then we can restrict to the yeah the we take any point in the boundary sphere and restrict to the disk there, and we have a foliation here. Now there's a small problem that this point P is no, so no, there's not a problem. This point P, it's in both manifolds. It's also on the boundary here. The problem is that this zero is not in the surgery because it's in the region that we cut out. Yeah, but these two, call it kind of running out of symbols. Prime prime. This P, we can just kind of take the straight line homotopy or of the sphere and get a concordant. So here's our obstruction class. We can get a concordant foliation on the sphere. And then we have an extension of this foliation to the disk. So it might have been better if I'd drawn a picture, but can I do it quickly? So here's our we're doing surgery on this sphere. And so we're cutting out this region, right? Here's some point P I choose. And so we have also this circle. And the whole thing with the surgery is we glue on kind of a cap here. And we have, the point is, the foliation surgery says we have the foliation here. And so that extends this sphere foliation. But this sphere foliation is concordant to the original concordance class, the original obstruction foliation.
I have a quick question.
Uh-huh.
Are there any, maybe I missed this, but are there any conditions on phi with respect to the foliation F when you do surgery foliation surgery?
You want it to be like transverse or something?
Mm-hmm.
No, because we're talking about Haefliger structures, we have a lot more flexibility.
Uh-huh.
So that's kind of the why.
Uh-huh, I see.
So in fact,
So it's not compatible at all. You don't have to say anything about phi with respect to F.
no, you're just pulling back a Haefliger structure. You can always do that.
Mm-hmm, I see.
So yeah, if you try and what I would say is people made similar definitions of foliation surgery in special cases, but they haven't gotten very far with them. And I think the kind of the issue is that they're making this requirement of regularity. So for example, there's one version where just in codimension one on 3 manifolds, if you have a codimension one foliation, I might say this wrong, maybe on any manifold, not 3 manifolds, then the Euler number has to vanish. Because you have essentially you have a vector field with no zeros. But if you do a normal sphere surgery, that's going to change the Euler number. And suddenly you get something that can't have a regular foliation. So one of these alternative definitions of surgery is you do these, what are they called? So some other kind of surgery that's more complicated to preserve this Euler characteristic number is 0. So okay, so conversely, theorem. And this theorem too really heavily relies on the fact that we allow as much singularity as we want. So if the obstruction class vanishes, then a strong foliation surgery can be made. So I won't go into the proof. I don't think I have time. But I will say that the construction is kind of very singular. um, uh, there is a theorem of Thurston that if you have a Hivliger structure and your normal bundle, you can find a embedding into the tangent bundle, then you can actually kind of straighten things out and get a regular foliation. So kind of when it's possible, you can make it regular, but sometimes these surgeries are just necessarily singular. So for example, you take the torus, this has that regular foliation I drew. You surgery it to the sphere. This doesn't even admit a regular foliation. So you're going to have to introduce singularities. It's unavoidable. So addendum, in case it's possible, if the obstruction vanishes and the normal bundle of F is trivial, then the surgery can be chosen. So, and it really is a choice. If you just choose a random one, this might not happen. Chosen so that F prime has, again, trivial normal bundle. Right, so if you start with a trivial normal bundle, you can preserve that by this process, which will be useful to me in a minute. So theorem for this is the Mather-Thurston theorem for k less than or equal to q plus 1. The kind of only thing, sk, foliation on the sphere is trivial if and only if its normal bundle is trivial. Okay. So at this point, I've thrown several statements at you, but if you put them together, you have this corollary. So if we have a foliation on a manifold M that's stably parallelizable and of dimension n less than or equal to 2q plus 2, and q is the codimension of the foliation. And F has trivial normal bundle. Then there exists a sequence of strong foliation surgeries. So M prime, F prime, all the way up to, no, the point is, we can get to the sphere. And so the idea is we use stably parallelizable, which says we can do surgery below the middle dimension. And then on top of that sequence, your spheres that you're surgerying along are of dimension small relative to the codimension because they're less than half. And because F has trivial normal bundle, so will the restriction of the foliation have trivial normal bundle. So is it clear what I'm saying so far? Right, so you have some SK into M, some element of the K homotopy group that you want to kill. You first of all can kill this by a surgery, and then furthermore, because this has trivial normal bundle, the pullback foliation has trivial normal bundle, and so by Mather-Thurston, it's in the trivial concordance class. So your foliation surgery obstruction vanishes. So you can do the foliation surgery, and furthermore, you can do it in a way that preserves having trivial normal bundle, and so you can do it again. You can kind of inductively go all the way to the sphere. That's the idea.
And hence your null coborded, is that right? Because that F on the sphere at the very end is itself, as by Mather-Thurston again, as a trivial normal bundle. So is that correct?
Oh no, we have to be a little careful. This, of course, is null cobordant, but this foliation might be extremely non-trivial.
I see. Okay.
Okay, so you notice all the surgeries happen below half, but
Yes.
this, so you would have to do a surgery on in,
Ah, right. Yeah.
and
Right.
we have no control there, and in fact, there's
course.
instructions, which how much time do I have left?
I'm not organizer. I was late. So.
About 10 minutes.
10 minutes? Okay. That 10 minutes plus questions, right?
Yes.
Okay, so then let me go to my next. This one will have to go fast, but here, this will give you maybe, if I get to an example of kind of that obstruction to closing up. So we have this classifying space, B gamma Q. I want to consider a slight variation. I'll call it F gamma Q, which is the classifying space of foliations with trivial normal bundle. Okay, so it'll be better to work with this one mostly. And so then it turns out this is an incredible space. Its topology is, we'll see. So first of all, this is not incredible. It's Q plus one connected. Lots of spaces are Q plus one connected, but the amazing thing is that this space topologically is absolutely massive. It's maybe bigger than any space you've dealt with before. So there exists surjections like in the 2Q plus one homology with integer coefficients to some real vector space, a positive dimension. Okay, so like just absolutely uncountably many homology classes. And a variation of this statement, which is maybe, so you can be sure I'm not kind of cheating with coefficients. And I think from talking with Sam, maybe this one is only rational. There's a surjection of the 2q plus 1 homotopy group. So maybe you need q coefficients. I'm not. I think that's what Sam said earlier. Um, so these, the way you kind of detect these is using these so-called foliation characteristic classes, which I don't have time to say in general, but let me give you one example. So there's this, the most famous one is the Godbillon-Vey. There's the Godbillon-Vey class. Given, so let me simplify a little. Let me take a regular transversely oriented foliation of codimension Q. There exists a form omega that's totally decomposable. That kind of characterizes the foliation. So the tangents of the leaves are exactly the annihilators, the vectors that annihilate this omega. If you take any tangent, any vector tangent to your foliation and hook it into this form, it'll kill it. And so by the Frobenius theorem, d omega is equal to eta times omega for some one form eta. So this is one way of stating the Frobenius theorem. And so what we can do then is take this eta and its differential and multiply it q times. So that'll be a differential form of degree 2q plus 1. And you take its cohomology class, the de Rham cohomology. And so it turns out this is well-defined. It's independent. There's several choices I made here implicitly, but the class doesn't depend on them. And furthermore, let's say you have a map of regular foliations, a transverse map. Then this Godbillon-Vey class will pull back nicely. And in fact, there's some kind of universal Godbillon-Vey class on this classifying space, B gamma Q or F gamma Q. And so let me just quote a theorem of Thurston. For each codimension Q, there's a family foliations M F lambda. Maybe let me take Q greater than 1. For lambda real numbers, such that the Godbillon-Vey number, the Godbillon-Vey class of F lambda, well, these are 2q plus 1 manifolds. Is there a question or? No, okay. The Godbillon-Vey class, that's a 2q plus 1 form. We can integrate it over M to get a number. That's the Godbillon-Vey number. And that's equal to R. So we have an uncountable family of foliations that all have distinct Godbillon-Vey classes. And well, these Godbillon-Vey classes are concordance invariances, which means that concordance invariants. So another way to say this is there's a surjection from the 2q plus 1 homology of B gamma Q to R. So kind of represented by these classes M inside of here.
That's integral homology.
Yeah, again, integral homology.
Cool.
So because you're just mapping, you're just pushing forward. What do we have? We have so M H lambda P gamma Q. You're pushing forward the fundamental class, and that's how you get this homology class. So that's integral. Let me just very quickly explain just what they live on. These are bundle foliations on the manifold M, which is sigma, some surface of genus more than 2 or more than 1. And then the torus dimension Q minus 1, and then it's a SQ bundle. So it's a trivial SQ bundle, actually. And you can give these by kind of giving a nice action of the fundamental group of this on the diffeomorphisms of this, roughly. But the point is that M is stably parallelizable. It's in fact parallelizable itself. But its normal bundle is the pullback of the tangent bundle to S, which is not trivial for most Q. So what you can do is you can modify the construction. So the fiber is, instead of SQ, you can make it there's a lot of different ways you can modify it, but you can, for example, take S3 times TQ minus 3. Did I get the dimension right there? Maybe Q minus 2. I'm guessing a little. So you can modify Thurston's construction to have this fiber, and this is parallelizable. So the modified F has trivial normal bundle. And so now you can apply that theorem I had on the last page and do these foliation surgeries, which preserve this Godbillon-Vey number. And so there exists this foliations on the sphere reasonably explicit, as explicit as doing surgery on this. Wait, no. It's the fiber. The fiber needs to be Q dimensional. So the minus 3 was right. Okay. There exists such that their Godbillon-Vey numbers equal all R. Essentially by modifying Thurston's construction. And it's a pretty small modification. So that's the same as saying, so now these are spheres in the trivial classifying space for foliations with trivial normal bundle. And the Godbillon-Vey gives you a surjection to R. Okay. Sorry, that last bit went a little fast. Maybe you have questions.
Great, thank you very much.
Thanks, Ben. Cool talk.
Any question?